So we'll now discuss progress guarantees, which are basically liveness guarantees, which ensure that an operation finishes. So the idea is like this, that if let's say a thread is holding a lock, it can get swapped out. And if it gets swapped out, then what will happen is that it will not get a chance to execute and release the lock. Then all the other threads that are waiting for the lock, they will wait forever if this thread does not get a chance to execute. That is why sometimes you may want to consider these lock-free algorithms where they don't have locks, but instead they rely on these atomic operations which execute something atomically, like an atomic fetch and increment, or maybe an atomic compare and swap. So even that is possible. So basically what happens with such kind of systems is that you do not use locks and you rely completely on these instructions. There is a theorem, it's known as the universal consensus theorem, which says that any concurrent data structure can be implemented without locks using these instructions only. All right, so there is a famous theorem like that. Of course, the implementation of data structure may be quite inefficient, right? We are not making a lot of guarantees on the efficiency of that, but it is possible to do. And in many cases, especially the ones that you use in modern C++, they are actually written, C++ and Java, they are actually written using such fast primitives, which many of them actually don't rely on locks, and large parts of the kernel, or a lot of kernel data structures also are fundamentally lock-free, in the sense that they use such instructions to get their job done. And the same data race, the theorem that we studied at the end of the last lecture, that holds over here also. So here there are 3 progress guarantees. So the first progress guarantee is that if n-1, if there are n threads in the system, n-1 threads stop. They just stop at an arbitrary point of time, stop. Is the nth thread guaranteed to finish the operation, whatever it may be, within a finite or bounded number of internal steps? Internal steps means internal steps of the nth thread, right? Is it guaranteed? Clearly, if you have locks, it's not guaranteed, because one of the other threads may hold a lock, it may go off to sleep, and if it goes off to sleep, then nth thread cannot make any progress. But if you design your algorithm in such a way that if just the rest of the threads keep quiet, you will be done. Like the example that we saw where you repeatedly run a compare and swap loop. Then such programs are called obstruction-free. Obstruction-free means if everybody else keeps quiet, I will reach my destination. That is called obstruction-free. You can have a stronger progress guarantee, which is called lock-free. This basically says that at any point of time, so the compare and set example that we saw, that was a lock-free program. It was obstruction-free also, but it was lock-free as well. Where you say that starvation is possible, in the sense one thread can starve, but at all points of time, at least one thread is achieving the final objective. It is reaching its destination, right? So someone is being successful, may not be me, but in the system as a whole is making a progress because some thread is being successful. That is lock-free. But lock-free programs can have starvation. They can't have deadlocks, they can have starvation. Wait-free means all the threads will reach their destination within a finite or bounded number of steps. Often the definition says bounded, right? And so that is wait-free, means that you will not have starvation. So if you just call fetch and increment, then it is wait-free, because your hardware guarantees that within a certain number of steps, fetch and increment will finish. If that is the case, your program becomes wait-free. But if you run compare and set repeatedly in a loop, right, waiting for when you are converted from 0 to 1, that is lock-free, not wait-free, because starvation is possible. So there is a hierarchy. It's very easy to see what it means. So maybe let's look at that. We'll come back to the previous slide. Every wait-free program is also lock-free, because wait-free is a stronger condition. And every lock-free program is also obstruction-free, because lock-free is a stronger condition. So few of the things that we have discussed, I would like to go over them once again. That no thread is allowed to hold a lock, because if it holds a lock and it goes off to sleep, then the only thread that is alive will not be able to make any progress. A lock-free algorithm is fast in practice, right? It is very fast in practice. That is why most of the time lock-free algorithms are used, even though they have a theoretical problem of starvation, which may not always manifest if the load is low. Finally, you have wait-free algorithms that definitely guarantee timely completion, but in general, they are slower than lock-free programs. Because, in exchange for the guarantee, a price has to be paid. And the price that is paid is that all operations become uniformly slow. That is why lock-free is in general used, or many data structures like queues and stacks and so on. So now what we will discuss is, we will discuss some of the more common synchronization mechanisms at a code level within the kernel. So we will discuss two advanced ones. Locks we have done. We will discuss semaphores and reader-writer locks. A semaphore is kind of like a lock plus plus. A lock has a binary state, right? The binary state is 0 or 1. All the threads try to convert from 0 to 1. And whoever was successful is deemed to be the owner of the lock. In the case of semaphores, it's a more loaded data structure. So a semaphore has a built-in count and it has a queue of waiting processes. All right. So semaphore in general is implemented at the kernel level. So you can think of it as a kernel level data structure, and it can have a user level library, but in general, it's done there. But again, there's no hard and fast rule. So the sem wait, what it does is it executes this chunk atomically, that if the count is equal to 0, all right, then you wait. So its connotation is slightly different from a lock, but the count is equal to 0, you wait. Otherwise, you set the count to count minus 1. Clear so far, so good? So this is good for a producer-consumer queue, as we shall see, but is the basic logic clear that if the count is 0, I wait for it to be non-zero. And then if it is non-zero, I decrement it, but I don't have to wait. The logic is clear. Similarly, the opposite of sem wait, which is like a lock, is a sem post, which is like an unlock. So again, this part executes atomically if the count is 0 and there is a waiting process. Then I wake up a process from the waiting queue. Otherwise, I simply increment the count and I accept. All right. So this is kind of tantamount. The reason I don't tinker with count over here is because I have waited someone. I would have set count to 1. Then the one that I would wake up would actually set it back to 0 with a count minus minus. Why do both? I optimize things. So I directly wake it from the waiting queue. So a binary semaphore is equivalent to a lock, but a semaphore clearly can do more in terms of implementing a bounded queue, which for us is an important data structure, as we shall see within the kernel. But the basic idea should be clear that 0 means a waiting state, non-zero means you're all set to go. But if it's non-zero, you decrement. So we'll now look at a reader-writer lock, which operates slightly differently. So it allows either one writer or multiple readers. But a reader or writer cannot coexist. Okay. So which basically, you can always read at the same time or only one writer. So you have two modes. A write mode, which has a single writer, no reader, only a single writer. Or a read mode, which only has readers. We need to switch between them in a fair manner, which is tough. So if you look at these read and write locks, then we will see that it is important to balance performance as well as balance fairness, because you have a lot of readers. The readers would want to read together And also, you can sustain high throughput if you allow many readers to go in together. But the issue is that will you delay writers indefinitely? A writer also needs a fair chance, right? It is just that when the writer writes, nobody else can be active. Fair enough, but does that justify indefinitely delaying a writer? Right? So what is the fairness? The fairness needs to be worked out. Okay? So we'll discuss reader-writer locks. So reader-writer locks, as discussed, the reader lock allows only readers to be there, and a writer lock allows only a writer, but does not allow does not allow any other writer or any other reader. So in many cases, especially if you are reading a queue, if you're just looking at the peak element, then you need a reader lock. You're not making a change. A change is being made in an NQ or a DQ. So that is like a write operation. So clearly you want to have one writer at a time, but possibly you can have multiple readers at a time. So for acquiring the read lock, you have to ensure that there are no writers, but other readers can be there. That's not an issue. And for acquiring a writer, you have to ensure that nobody is there, right? No reader as well as no writer. So we'll create two internal locks. We'll create a read-write lock and just a read lock. So let us look at each of the functions. So let us say I want to get a write lock. If I want to get a write lock, which means that I am a writer and I want to write, then I will simply lock. So let's assume a macro called lock is defined. I will get the read-write lock. And let's assume that this means that there is no concurrent thread there. No reader as well as no writer. Okay? And similarly, if I want to release the write lock, then I will do an unlock and I will release the reader-writer lock. Alright? So this basically means that now everybody is allowed. So far, so good. So this is very simple for a writer. It gives you exclusive access. So this part is simple. The complexity will come when we discuss the reader. So when we discuss the reader, here is what will happen. If we get a read lock, then let us see what we want. If other readers are there, we have no issue. That's perfectly fine. But if other writers are there, then there is absolutely an issue. So what I will try to do is that I will first try to lock read lock, which I can. So this is not conflicting with the writer because I have not made any permanent change. So I will try to lock the read lock. After that, if the number of readers is 0, all right, if the number of readers is 0, this means that there is no reader. Because if it is non-zero, it means that there are active readers. So there cannot be a writer. But if the number of readers is 0, then there are two possibilities. Either the lock is empty or there is a writer that is alive. So then I will try to lock the read-write lock. If a writer is alive, this function call will wait until the writer exits. All right. So otherwise, if there is no writer, I will get the lock. In any case, I will come here. I will increment the number of readers. That has to be done because as a new reader, I am registering. And then I will unlock the read lock, but I'll still hang on to the read-write lock. This ensures that because I am a reader and now I am in, no other writer can subsequently come in. Does that make sense? That I hang on to the read-write lock if I am the first reader, such that no other writer can come in. All right, so we will look at what we do read-write lock with the read-write lock when we release, but this is how it works. All right. When we release the read lock, then what happens is that we lock read lock. And so this has to be done because this is protecting the reader's variable, right? So you'll have to lock read lock in any case because the reader's variable is associated with this. I do that. And because something is being released, I do readers minus minus. If the number of readers becomes 0, then potentially a writer can be allowed. So I unlock read-write lock, otherwise I keep hanging on to it. All right. So it is very well possible that one thread that actually locked read-write lock, some other reader thread is unlocking it. That is absolutely possible. So once this is unlocked, if there are writers, they can go in, and finally we unlock the read lock. So this is how you get a reader-writer lock. So clearly fairness is an issue. The reason it is an issue is because readers can keep coming in, and because there is nothing to stop them. They will keep coming in, and a writer can start forever in this design. So in this design, it is fair for readers, but it is not fair for the waiting writer. Nonetheless, this is an example of a two-lock situation known as a reader-writer lock. So next, we will use such basic primitives to design a higher level structure. And the higher level structure is a queue. And the queue is very, very commonly used in operating systems. It is one of the most commonly used data structures, if not the most commonly used data structure in the kernel. These are typically producer-consumer queues where items are added by producers for inter-process communication, and consumers remove items from the queue. And queues themselves could be of many different types. You could have a bounded queue, for instance, where the size of the queue is limited to, let's say, 10 items. More than that, unless the consumer consumes, the producer cannot add. That's a bounded queue. You could have cases where there's only a single consumer, multiple producers. You could have a case where there's a single producer, multiple consumers. Or in the general case, multiple producers, multiple consumers. You could also have a synchronous queue. The synchronous queue, what it does is that, let's say the queue is empty, the consumer will wait for something to be added. In an asynchronous queue, if the queue is empty, the consumer will just return it's empty. So nobody waits, right? And let's say if it's a bounded queue, the producer will wait for space to be created. But if it's asynchronous, the producer will say, look, I could not add because the queue is full. What can I do? Right? Nothing can be done. All right. So you could have synchronous variants. You could have asynchronous variants, bounded variants, unbounded variants. So a lot of variants are possible, but this is like a very core data structure. And this has to rely on synchronization because it's a parallel data structure. It's a concurrent data structure, correct? And you would want some kind of a progress guarantee, right? Even if you are using locks, let us assume that even with a lock, you are able to release it in a finite time. Some progress guarantee is needed, right? Either obstruction free or lock free. That would be good to have. So as I have said, practically what makes sense is a bounded queue because you don't want anything to be unbounded in practice. It is clearly used by a large number of kernel subsystems, mostly device drivers. You read something from a device, put it in a queue, like that. And this has to be concurrent because a single queue is accessed by a lot of entities. Definitely by the producer and the consumer at the same time, if not more. So what we will do over here is we will look at 5 separate queue-based examples of, we'll first look at a single producer, single consumer queue. It is possible, so whenever you have a single producer, single consumer, creating a wait-free queue is very easy. So this is, mind you, wait-free. So every operation will complete in a bounded number of steps. This is very easy to do. But the moment you have more than one producer or consumer, then creating a wait-free queue is somewhat harder. So then we will first look at one solution with a simple busy waiting lock, one solution with semaphores, another improved solution with semaphores, and then a solution with reader-writer lock. So whatever we have designed up till now, we will look at all of them in real code, right? So the first example, so we'll look at it example by example. I will explain the theory first. We will look at, so the way we will proceed is that we have 5 queue-based examples. I'll tell you the theory, I'll show you the code. So even when you go through the slides, you are advised to first understand the basic theory, look at the code and run it. Unless you run the code, you will not get a practical feel for how it's working. All right, so running, working code is something that is the most valuable, right? So to ensure you understand it, let's look at it. So stdatomic.h is a library of atomic integers, mainly integers, characters. And the most important are atomic load and store, which provide those guarantees that we discussed, that they are synchronizing instructions. So they provide a happens before guarantee. So then there are many more operations that you can do, like fetch and add. Fetch and add means you fetch a value, add something to it and store it back. All of these operations happen atomically. Something like x is equal to x plus 3, this entire thing will happen instantaneously. The next is test and set, which means if it is 0, set it to 1 and return 1. Right, but if it's 1, you will always return 0. Then compare exchange, we have seen that. So all of these atomic operations are actually sequentially consistent, but as I said, we are not in a position to fully understand how that is done. But assume for the sake of simplicity, well, not for the sake of simplicity, in reality that is the case. So let us actually design a piece of code that will use these atomics. All right. So we will look at the first piece of code. So it is a wait-free queue with a simple single consumer, single producer situation. So we will look at these numbers. We'll look at this piece of code. So what you can see over here is that we have a for loop with 2 iterations. And in every iteration, we allocate an integer pointer. And furthermore, what we do is that if, let's say, and then we also allocate a function pointer. So if it is the first iteration, which means I is equal to 0, then we assign one of these 2 functions, enqueue function and dequeue function. So if it's 0, we assign it the dequeue function. And if I is equal to 1, 1%2 is 1. So the first argument, the enqueue function. So what we actually do is that we create a pthread, assign it either the enqueue function or the dequeue function, and assign it this IDs 0 or 1. All right. That is all that we do, which basically what we are doing in very simple terms is that we are creating 2 threads. One of them is the enqueuer, one of them is the dequeuer, because we have one enqueue and one producer and one consumer. And the enqueuer does its job via the enqueue function, which is enqueue func, and the dequeuer does its job via the dequeue function, which is dequeue func. All right. So if we go to the enqueuing function, then this is what we do. So what we do is that based on the argument that is passed, we create a local variable called thread, and we use that to seed a random number generator, right? So this is fine because we want random numbers to be generated, and we want the random number to be seeded by the thread ID such that they are different. Fair enough, we do that. And then for num iterations, where num can be a large number, I'll show you what it is at the moment. Num is defined as 25, but you can make it 1000, 10,000, doesn't matter. So then what you actually do in the enqueue function is that you generate a new value, which is a random number, %10, which means it is between 0 and 9. You generate a new value, you enqueue it using the function enqueue, and you take a nap. Nap means you wait for a random duration. Then you enqueue again, you take a nap, you enqueue again, so on and so forth. So let us look at the nap function first. The nap function is easy. So here what you do is, so struct time spec is the standard C structure for time. And so we generate a random number, then percentage it 100 with 100, which basically means it generates a value between 0 and 99. That is the number of milliseconds we wait for. Then of course we multiply this into 1000 into 1000, because the unit of this is supposed to be in nanoseconds. and we sleep for this duration. So we call the nano sleep function, which basically means that we go ahead and we sleep. All right. For this duration, we go ahead and we sleep. So this is like taking a nap. So the most important, so the DQ func also works in the same manner. Fair, of course, in this case, we again seed the random number generator with a different value, but this will not be used. Well, it will be used inside nap. So this ensures that when you are taking a nap, you are actually taking a nap for different durations and the random numbers are not the same. Because if the seed is the same, then what will happen is that the values that it will generate will be the same, because it's a pseudo random number generator. It's not a true random number generator. Hence, you seed it with different values. So you take a nap. So basically, the idea here is that you NQ a value and you DQ a value. So the Q property is that the first in, first out order has to be maintained. So let us now look at the NQ and DQ functions, where essentially the meat of the logic resides. So let's look at NQ. So we need to, slightly open our minds and visualize the Q a little bit. So let us say that the Q has a head pointer and a tail pointer. Is that clear? It has a head and a tail. So we use atomic operations. We have 2 pointers. So you can see they are defined here, atomic head and tail, because we are actually designing the Q as a circular Q. So we'll see in a second what that means. So the current head is the value of the current head, and current tail is the value of the current tail pointer. So we check if the Q is full. All right. So then I have a new tail, which is 1. Increment current tail is basically 1 plus current tail in a certain sense. So let me draw a diagram. It will be slightly clearer what we mean by a circular Q and how it is implemented. It will make things way clearer. So let us try to understand how you would implement a Q in practice. So you'll actually create a circular Q. So you'll create a circular Q out of a regular array only. All right. How will you do that? Well, nothing. You just unroll this array. So this is 0. All right. So if you want to go to the next entry, all right. So let us assume that going to the next entry. So which direction do you want? Clockwise or anti-clockwise? For going to the next entry? Fine, clockwise. So if that is the case, and you want to go to the next entry, you will number this 0, this 1, so on and so forth, and you will number this n minus 1. So the going to the next entry is basically, if let's say the current entry is 1, the next of entry is basically e plus 1 percentage capital N. All right. So which means if it is 4, it will go to 5. If it's 7, it will go to 8. But if it is n minus 1, it will go to n minus 1 plus 1 percentage n, right, modulo n, which is 0. All right. Now what we will do is, let us assume a current state of the Q, where let's say part of the Q is full. This entry is full, this is full, right? So you will have a head pointer and you will have a tail pointer, right? Where the head is the head of the queue. So if I have a long queue of people standing, then the first entry to be dequeued will be at the head or the tail? Head of the queue. And if you want to add something, where will you add it? You will add it at the tail of the queue. So what happens is that this is the head. All right. This point is the tail. If you want to dequeue something, all that you need to do is that you need to assume the queue is full. You will extract the element at the head, and the new head will be inc of old head, where inc of any entry E does this make sense? So basically the head from here will get assigned to this one. All right. Similarly, if I want to, so this is the case when I want to DQ, right? I stand corrected. So when I want to DQ something, I will go to the head and I will increment the head using this logic. It's like a modular increment. Similarly, if I want to NQ something, which means I want to add something to the queue. In that case, where will I add, on which side? The tail side. So I will create a new tail, right? Which is nothing but inc of old tail. And I will add the new entry here. So far, so good. So in this manner, I can keep doing it. So it doesn't matter. So this thing can kind of rotate and it can straddle the point 0. It doesn't matter. As long as the number of entries in the queue is less than the total number of entries in a circular queue, you are fine. All right. So this is a case where dequeuing something is tantamount to incrementing the head, and enqueuing something is tantamount to incrementing the tail. All right. So this is very simple. If I have a single n, even if I have multiple NQers, DQers, all NQers are going to contend on the tail and all DQers are going to contend on the head. And this is a nice way of implementing a bounded queue. All right. So far, so good. If things become full, then the tail will come here. Correct? That is when things are full. You can't NQ anymore. That means inc tail should be equal to head. That is your condition for fullness. That is exactly what we are checking here. That if new tail, which is inc of current tail, incremented current tail, if that is equal to the current head, that means that the queue is full. That means that the queue is full, so you return -1. Does this make sense? All right, so that just follows from the diagram that we drew. Next, if there are, then you check if there are others, because there are no other NQers, here is something that you can do very easily. What you can do, because in this case you have space and you know that there are no other NQers, it's a single NQer situation. So what you do is that at the current tail, you basically store the value val. All right, so you assume that the current tail is actually not pointing to the current tail, but the entry just after that. All right, so basically what you need to do is you need to make a small change in the diagram where you say that, so let's say if you consider this situation, the tail is actually pointing to this point, which is the first free entry after that. So what you do is that at q current tail, you write the value val which you want to write. And then at the tail, you write the value of new tail, which is one incremented current tail. Does that make sense? And then you say that I was at the current tail value, I was able to add val, you print it to your command line. So this is possible. Why? This is possible because there are no parallel NQers, there is no competition. So what you do is that at your tail point, right, which is the slightly amended definition of the tail that we just did, which is not the last entry, but one after the last entry, you add the value. All right. And then what you do is that you increment the tail pointer. All right. Sounds good. So this is what you do. And this something exactly reverse is done at the point of dequeuing. So here also you read the current head and current tail. And then you find a new head, which is essentially modular 1 plus the current head. In this case, you have to check for emptiness. You have to check that they are not the same. So when they actually become the same, the current tail and current head will become the same because they initialize to the same value. All right. So if they are the same, you return -1 saying it is empty. Otherwise, you can go to these 3 lines. Because there are no other dequeuers, you can get away with this. If there are other dequeuers, this piece of code will not work. So here what you do is you do an atomic load. So you read the value of the current head, right? So that is your head of the queue. That you read and you return and you replace the current head with a new head and you print. That is all that you need to do. All right. So you have a fully functional piece of code for a single enqueuer and a single dequeuer, which is parallel. It runs in parallel and it's a bounded queue. And the greatness of this design is that it is weight free. Why is it weight free? You kindly check. There are no locks. So it is lock free for sure. Second, there are no loops or something. So there is no possibility of starvation. So let's say there is an enqueuer. Is there anything to stop it? There is nothing to stop it. Since there is nothing to stop it, there is no possibility of starvation. So this is a weight free queue, subject to the fact that you have a single enqueuer and a single dequeuer. The moment you start adding more, things will start becoming more complex. So we will look at that. But at least, this is one example where an elegant solution exists. So even for a multi-producer, multi-consumer case, elegant solutions do exist. But there the code is way more involved than this. Right? So that's the reason we will not discuss it in this course. So there is one important point to understand. So let us go back to this thing. So in our amended definition of a queue, so we have slightly changed things. So we are saying that the head points to the first valid entry if there is one. And the tail does not point to a valid entry. The tail is the next entry after the last valid entry. So this gives us very interesting properties. One property is assume that we keep on dequeuing entries. Every time we increment the head, so ultimately we'll do this. And after a long sequence, ultimately the current head and current tail will become the same. That indicates emptiness. What will happen is that if we keep on incrementing tail, right, then we will reach this point, which will be current tail. And a new tail, so the current tail will be this point, there is no issues. All right. The next time that we do, the current tail will be this point. And this clearly will be an empty position, but we will not add anything here. So it is important to leave one of those entries empty in this design. In our slightly amended design, we will change the definition of a tail. And the reason is because in this case, new tail will be equal to head. And when new tail is equal to head, we will interpret fullness. All right. So basically, that is why it is important that if, let's say, n is equal to 1000, the maximum size of the queue can actually be 999 precisely because of this issue, that we would like to keep one of the entries vacant such that we can differentiate between an empty queue and a full queue. Right? That is why it is necessary in this design where we amended the definition of a tail pointer to actually differentiate between both the cases of emptiness and fullness. So given that we have seen a weight-free queue, let us move to a queue with locks. So clearly the issue with the weight-free queue was that we had a restriction that we'll have a single enqueuer and single dequeuer. That allowed us to get away with a lot of assumptions. But in this case, if you have multiple enqueuers and dequeuers, this same trick will not work. We have to use locks. So what we can do is that we can use a regular pthread mutex to just acquire a lock, and that will do our job. Right? So you just acquire a lock on NQ, you acquire a lock on DQ, and that will do our job. So Linux actually uses slightly smarter locks. So locks are called mutexes in pthread, mutex for mutual exclusion. But Linux uses something called a futex. Think of it as a future mutex. So it's called a futex. So what this does is that this does busy waiting for some time. But as I have argued, it is kind of wasteful work. Because all that what are you doing? You're only checking the value of a variable. And essentially, you are spending energy, you are spending time, but you're not achieving much until the lock is released. It is much better that you wait for some time. Then you let the OS know that, look, I'm not getting the lock. Kindly context switch me and allow some other process to run. This is known as yielding, where you tell the OS that, look, I am not able to make progress. I yield. Yielding basically means bring in some other process in my place. So what we'll do in the next lecture is basically start from here. So we will start from this point where we will look at all kinds of synchronization, which is basically locks. So we'll look at locks, we'll look at semaphores, which are extensions of locks. We'll look at reader-writer locks, something similar to what we have written. And then we will look at other kinds of synchronizations, which are slightly more complex in character, like condition variables, barriers, and phasors. So this is what you can expect in the next lecture. So the plan is that after going to this point, we will go into kernel level synchronization, and that will naturally open a path to scheduling problems. All right, so it's important to understand basic synchronization before understanding kernel synchronization, and that will, as I said, open the door to advanced scheduling.